Hello, good morning, good evening, good afternoon, everybody, wherever it might be. And bom dia, Brazil. It is my great pleasure to welcome my nephew, Gilles Gonçalves de Castro from Floripa, who will talk about our joint work with Francesco and also with Ralph. And you see, for a change, we host your talk from the oldest Polish university in Krakow. So we've been waiting for your talk for over 660 years. So it's time that you give it to us. Go ahead, it's all yours.
Okay, so thank you, Piotr, for the introduction. So as you said, this is a joint work of Francesco and Piotr. Most of all, I'm talking. And then the last part is still work in progress of Hofmeier. And then, yeah, I'll explain a little bit this at the end of the talk. So I'm going to talk about relation morphs and directed graphs. So just a little bit of motivation on why we wanted to study this. So the idea is that graph sister algebras are a very interesting class of algebras, and they are algebraic counterpartly left graph algebras also very interesting because the algebraic properties of these algebras can be seen in a way from the graph. And it has a lot of applications. It has applications in symbolic dynamics, noncommutative topology, and classification. Myself, I started working for graph system algebras from the point of view of dynamics, a little bit of working with KMS states and things like that. But then there are also a lot of other approaches to graph system algebras. And as I said, the interesting is that we can really see these algebras as, just a second, yeah. We can really see these algebras from their graphs. So there are a lot of things that we can talk about the graphs, the algebras using these graphs. And for us, the main goal of this project in general is to define a notion of a morphism between graphs in the way that the construction of a graph system algebra or it's the left graph algebra is functorial. And then there are two different approaches that Piotr has done with his collaborators that appears naturally in examples. But the problem is that in some examples, the notion of the morphism gives a covariant functor, and the other is a contravariant functor. So there is the question on how we're going to unify these notions. And for the last part of the talk, when I'm going to talk a little bit about groupoids, so we define this notion of relation morphism between graphs, and we prove the functoriality. But there are some examples, even if we start with this relation morphism and get an isomorphism between sister algebras, sometimes the inverse is not described using this relation morphism because, as we're going to see, we need something extra to do it. So that's the main goal and what I'm going to try to explain today.
At the very beginning of the game, you already scored a goal. So it's 1-0 for Brazil.
Yeah. Okay. So of course, a lot of people are familiar with this notion, but just to recall, when I talk about the graph, we talk about graph from the point of view of operator algebra, so it's a directed graph, and we usually think that this is a quadrupole of two sets and two functions from the sets E1, which is the set of we call a set of edges, and then you have this E0, which we call the set of vertices, and then this source and target maps, kind of the beginning of an arrow, and then or an edge, and then this is the end of an edge. There are other notations. Before starting working Piotr, we usually use R for range of the edge, but well, this is a notation. And we're gonna need the notion of a regular vertex. So a regular vertex is this one, there should be S minus V of P. So there should be a P here. So this set is finite and non-empty. So happening, this is called a regular word. So if it's empty, it's a sink. If it's infinite, it's infinite emitter. And if it's finite and non-empty, we call it regular. So here I'm already kind of saying what kind of convention I'm using, because if I were to use the other convention, I would use the target here. So my work with Hofmeier, we are using the other convention, so it's gonna be a little bit. I hope at the end I corrected to this convention, but there might be something that I missed. And it's going to be important for us, this set of regular vertices, which we're going to just call reg of E, so reg for regular. And again, here there are other notations for this set, but this is the one I'm going to use today. Okay. Also important is the notion of paths. So a path on a graph is just a concatenation or a sequence of edges in such a way that the target of one edge is the source of the next one. Again, this I already show with the convention that I'm using. I don't talk here about, well, here we are talking about paths of length n, but we can easily do the same thing for infinite paths. So just instead of a finite sequence, we just take an infinite sequences, and then the same relation goes for all I. And then we can define the source and the target of a path. So the source is just going to be the source of the first edge of the path, and the target is going to be the target of the last edge of the path. If the path is infinite, we can also talk about the source, so it's just the first one, but then if it's infinite, there's no target. That doesn't end. And just for a matter of notation, sometimes this is gonna be important. We're gonna use the E just to remind that this is the function, the original function that we are using from the set of set of edges to the set of vertices, both for T and S. And when you use this PE or PF, so this is paths on E. So this is sometimes we need to take prime images of vertex with these maps, and it's different if you look at paths or if you look at edges. We can also think a vertex as a path of length 0. This is something that sometimes I think about, but I never seen this in any definition of graphs, but you kind of need the set of vertices and the set of edges to be disjoints. Or if they're not disjoint, we consider them to be disjoint because you cannot have a path of length 0 and 1 at the same time. So
yeah, they are disjoint. Yeah.
so
By
there's
the length assumption, yes.
Yeah. And then for a vertex, the source and target is just the vertex itself. And we in this talk, I'm gonna use this FPE, so finite paths of E is the set of all finite paths. In other reference, it also appears E star as the set of finite paths, but here I'm going to use FPE. Okay, so also when you have paths, you can concatenate these paths. And in order to this concatenation to be a path again, we need that the target of the first path is the source of the next one. So then we just use the concatenation at x prime to be the concatenation. If x or x prime is a vertex, then it's kind of an identity. So we do not write xb, we just write x if x prime is a vertex. Similarly, if x is a vertex. And there's this notion, kind of this kind of this initial subpath, or sometimes I call it the beginning or the initial segment. So whenever you have this concatenation, this first pass we just call an initial subpath of the concatenation. And then we can define a partial order on on paths by using this initial subpath relation. So x is more or less weak on x prime, if x is initial subpath of x prime. For people that are familiar with inversing group, actually the order that appears as for the inversing group of a graph actually is the other way around. It should be x is greater or equal to x prime if this happens, because for inversing groups, the relation that appears is kind of inclusion of cylinder sets, and then the less information you have about the cylinder set, the bigger it is. So the cylinder set of x is actually contains the cylinder set of x prime, so the relation is in the other way around. But here we're just going to use this, well, smaller paths going to have to be a smaller, well, smaller in the length, is going to be smaller in this sense. And sometimes we're going to need this strict order. So sometimes we want this to compare two paths, but we want them to be different. So we just remove the bar at the symbol. And also sometimes we need either one of or the other. So if they are comparable, then we use the tilde symbol to say that they are comparable.
Sorry, the symbol is dangerous since it is not an equivalence relation, yes?
No, it's not. It's not an equivalence relation. Yeah. Not sure if it is.
Well, it might be if they are equal. If one is greater or equal than the other, and the other is greater, yeah, that is an equivalence relation.
No, it means that this partial ordering is in fact partial ordering, but this.
Okay, yes.
Yes, it's
Sorry.
just being comparable.
Okay,
Yeah, being comparable is not an equivalence relation.
yes.
But that's a notation that we use. I'm not sure exactly why you use this. It appears somewhere else. To check it.
Yes, I just wanted to clarify it since this symbol is usually reserved for something which is equivalence relation, and therefore it could be misleading, but
yeah.
Okay, if we stress it, then
It's not,
yeah.
Okay, and then I'm not going to go through all the construction of the algebra, I'm going directly to the definition of left path algebra, but then we can, in our paper, we go through all the construction of the path algebra, then the compath algebra, and finally the left path algebra. The path algebra is the easiest one. We just take the pre-algebra generated by the edges or the paths, and with multiplication the concatenation here exists, otherwise it's 0. And then for this one we could go for the extended graph, which adds a copy of each edge or in the other way around. But yeah, as I said, I'm gonna do it directly. So for the left path algebra, we take any graph and take a commuted dimensional ring.
All appearances of this E should be as a subscript, yes?
Yeah.
In the third point you have, yes?
You missed with one dash in LaTeX, I think.
Here, yes. Yeah, and
Okay.
here, yeah.
Up here.
Yeah, so
Brazil, Poland 1-1 now.
Sorry?
The score of goals, Brazil versus Poland, is 1-1 now.
So as I said, there is a definition use the field, but we can define for any commutative diameter ring. Yes, we could even weaken this condition, but usually this is what we use. And then we use this notion of a universal algebra generated by elements and relations. And then we have a copy of vertices, and I have two copies of edges. So one is kind of the original edges, and the other one is usually in the left path algebra book or other papers, there's no S, just E star, and then this star is considered a ghost edge, which goes in the other way around for the extended graph. But here, let's just think as they are symbols. And
So one detail, excuse me, R, there should be T instead of R, yes?
Yeah.
Target and not range, yes?
Yeah. R or T, yes, is the same.
Yes. As I said, that sometimes I use R, and I think I prefer from another file, and this should be E, and
Sure.
yeah. So we want these projections to be orthogonal. We want them to be idempotent and orthogonal. If you consider a star algebra, we also I'd ask them to the star to be itself. For the relation with the projection and this S, it's kind of concatenation of paths. So if you start the source of E and concatenate E, just E, and same thing with E and the targets of E. And the star, as I said, the star is kind of the ghost edge, which goes the other way around. So the source of E star should be the range of E, and the vice versa. And then we want if you go for, I come from sister algebra, so I think about this final projection. We want the final projections to be orthogonal, and here is something that this is if you put SF and SE star at the end, so this is going to be the final projection being orthogonal, and then the initial projection is the projection on the target of E. That's why some people don't like this. They prefer to use the source because this is the initial projection, so the initial projection will be from the source. But anyways, and finally, for regular vertices, we want the projection or this idempotent to be this sum of the final projections of each edge that starts with B. There's a way of thinking this in a kind of a dynamical way. So this SE is just kind of gluing E at the beginning of a path, and the SE star is kind of removing. So removing is kind of this subshift map that we have. And then the projection is just gonna be the characteristic functions of singular sets of paths starting with B. But anyways, so this is the light path algebra, and then for the sister algebra, we can use this notion of we have the net. As I said, we can define a star for projections to be themselves. Of course, we want the star of SE to be SE star E, and then the star of the star should go back here, and we take any involution R. If there's no involution, just take the identity of use complex numbers with conjugation. And then there's an involution for light path algebras, and then we consider star algebra when you take the complex numbers. And then for the sister algebra of E, we just take this universal sister algebra of the light path algebra. Or we could just say that the sister algebra of E is the universal sister algebra generated by this same sets and same relations. Of course, then in the sister algebra set, we need to add the star relations. And sometimes we can even remove this set because it's already generated as a star algebra, so we don't actually need this one. And this is the definition that appeared for light path algebra. For graph sister algebra, it's usually a little bit different, but the definitions are equivalent. If you want to go for the cone path algebra or in the sister algebra side in toplet graph sister algebra, we just remove this last condition here. And then we have this other version. But I'm not gonna talk about them today.
Yeah.
Okay, so this is the definition of the algebra. As I said, our goal is kind of define morphisms in such a way that there's kind of a functor on the category of graphs and a certain suitable morphism to this. I'm going to talk about sister algebra, but could do the same thing for path algebra, for algebras in general. So for me, the category is going to be from the category of graphs to the category of sister algebra. And the category of sister algebra using star homomorphisms as morphisms. So we're not going to use correspond or something like that. Okay, so the first notion that we can define for homomorphism graph, and this is the definition I guess people from combinatorics use, is just a pair of functions, one from vertices and the other from edges, they are compatible with both the source and the target maps. So if you take the source of an edge and then you apply the map on vertices, or if you take the map on edges and then you take the source, it should be the same thing for the targets. And we're gonna call this category of graphs and homomorphism of graphs by OG. I don't remember why is it O, Piotr? Is it for
Ordered, probably.
Say it
original?
again.
Ordered, yes?
Yeah, I think but because of ordinary, this was
Ordinary.
yeah.
Not ordered.
No.
Okay, it's called directed. Okay.
Yeah. And I'm not gonna define this subcategory. There are a lot of things that we need. I'm gonna define it in general for relation morphism later. Then this, in a way, it's gonna be appear there. But I think this P is for proper, TB is targeted bijective, R is for regular, and the C I don't remember. What is it?
Contravariant. Because we had R in both cases. So it's contravariant regularity and covariant regularity. But I like to explain that we had to be really high when we invented this terminology. But it was pandemic time, so you can forgive us.
Yeah. So there's a subcategory of the. I guess before I go to the subcategory, I'm just gonna explain the formula. So this is the contravariant functor. So we're gonna have a morphism between E and F, and then the star homomorphism is gonna be from C star of F and C star of E. And then here the idea is just taking prime images. So you want
V is missing, yes?
should be a V there, yeah. Pre-image of V, and here should be pre-image of F as well.
Yes.
So
it's very hard to write with a touchpad, so I will not do it. Okay, perfect. Yeah.
So the idea is taking pre-images, and then we take the sum of the projections as associated with V, and they send the same thing for the edges. So this proper is, well, you identify it seems to be finite to make sense, and then we want this to be star homomorphism, and we need to satisfy that condition on the last condition that I said for regular vertices, and then that's where all this comes from. That's why we need all this particularities of a homomorphism to these two to work. But there is this subcategory. So there is this unique homomorphism given by phi, and this association is functorial. So there's a functor from this category of contravariant regular target bijective proper homomorphism graphs, and the category of sister algebra with star homomorphism. Or if you want to use left-path algebra, then the category of algebras. Okay, so this is one of the notions that appears. This is the one that we use for inclusion of graphs. So an inclusion, there's this notion of an admission inclusion. An admission inclusion just a morphism that is an inclusion here in this category. So this is one of the place that appears. This one simple example. I'm not as proficient as Francesca in drawing in graphs, so I didn't draw it here. But there's a very simple example. So if you take the graph that gives the algebra circle, and then if you take the graph that gives the top its algebra, then there's a natural inclusion between these two graphs, and this is going to be an admissible inclusion, so it's a morphism in this category. And then this star homomorphism is just going to be the quotient map, the usual quotient map between the top side to the circle algebra.
So let me make a quick comment, if you don't mind. So this inclusion, which we call admissible, is incorrectly called in the literature quotient graph, which is completely idiotic because you are taking a subgraph. So it doesn't make sense. What is a quotient is a quotient map between sister algebras. That's a quotient map, but the graph is not quotient, it's a subgraph. And another thing which I would like to mention is that these axioms, C, R, T, B, P, O, G, were completely independently and much earlier discovered by Katsura, and in the more general context of topological graphs. So when you take Katsura's work, put discrete topology, then we recover what Mariusz and I found some years later, being completely unaware that it happens. And here, that it was already known to Katsura. And here somehow this subtlety really lies in target bijectivity, is telling you what you have to satisfy in order to go beyond injective. So that's sort of the taste of this category, is how to go beyond injective. And here what really a problem is to satisfy the first constrictor relation. I don't know which number it was on your slide, but it is this relation, you know, E star F is equal Kroneker's delta EF P of E, okay?
We'll play the fourth relation in there.
I have a question.
Yes.
The last line, moreover, this association is functorial. I'm not sure if I understand. What is this about?
So the idea is there is a functor from this category.
You said that this is a subcategory.
Yes.
So this means that at least on the level of morphisms and objects, you have...
Yeah, but it's, Tomek, it's a subcategory in OG. It's a contravariant functor to the category of star homomorphisms and C star algebras.
Yeah. So there is this category C, R, T, B, E, O, G. And then you go to the category of C star algebras.
And star homomorphisms.
And star homomorphisms. So the idea is that you take a graph here. The homomorphisms, the morphism of these categories is this homomorphic graph satisfying this extra condition that I'm not defining here. And then you take a graph and you go to C star algebra, and then you take this homomorphism and you take it to this P star. So this is the functor. So
here the situation is even better, because these are you can restrict the category of C star algebras to the category of U1 C star algebras, because when you take the canonical gauge action on a graph C star algebras, then these morphisms, these star homomorphisms, are U1 equivariant for the gauge action.
Yeah.
So it goes into even a richer category, and better still, if your C star algebra if your C star algebras happen to be unital, then in fact you go into unital star homomorphism, and none of these two things is true when we go to the next functor.
And sorry, question maybe to Piotr also. The corresponding on the level of graphs, the corresponding notion for getting something unital is what?
It's having finitely many vertices.
yes.
Vertices. Okay.
Yeah.
Okay.
Yeah, and here, because you are taking preimage, so if I sum all vertices and I take preimage of all vertices, I get all vertices.
Okay.
Whereas later on, when you go to the covariant one, you must be injective on vertices, but you can have 5 vertices on the left and 7 on the right. You are still injective, but one is not mapped into one. And the example is like you construct compact operators. You include matrices in bigger and bigger matrices, but this inclusion is by extending by 0, and so it's not unital. Okay. And plus, we will no longer preserve a length of path, so we will not be equivariant. But here we are both equivariant and unital when units exist.
Okay. Thank you.
So this is the functor. So you take a graph and go to the C star algebra and take a morphism phi and go to this pi star.
Tomek, are you happy?
I'm still digesting this, trying to understand this in categorical terms. So first you are defining some class of morphisms.
Yes.
Phi. By the existence of this unique star homomorphism. And then you
No, of course not.
There are a lot of properties of homomorphism that we ask. I'm not giving here because I want to give for relation morphism later. So this is the work of Piotr and Mariusz.
So this is, okay, so this is not a definition of this
No,
subcategory?
it's a
No,
theorem.
it's a theorem. It's a theorem. There exists a subcategory.
Such that if, not, it's not a definition. You're not reading it properly.
It's going to be a little bit more clear when I define the correlation morphism later. But there are a lot of properties of homomorphic graphs that a lot of jacks that we want to put it that
but you are not saying about, for instance, uniqueness of this subcategory.
No. Tomek,
So what is this about?
Look, it would help if there would be a comma here. There is a subcategory blah 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 such that if da 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 belongs there, comma, then there is a unique star homomorphism blah 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 such that.
I see. So it's a different.
It just, without commas you can.
Yeah.
Okay.
It's ambiguous.
Yeah.
Without commas, it's ambiguous.
Yeah.
Okay.
That's why I put the commas.
The existence is not really the important part, I guess, is that the important
Factoriality is essential. Yes.
The factoriality is essential, and then this adjective, which I should give the definition if I want to go the details, that would be the important part. Okay.
Okay. So before you have some examples, before you have some characterization of this subcategory, you know almost nothing about this in this theorem.
But we define this category. He is telling you the seventh time that this is a concretely defined category. We axiomatize it. Morphisms have to satisfy blah, 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 blah conditions.
Yeah.
Which he's not spelling out.
Yeah.
Because he said it many times.
Yeah.
Okay. But to be concrete, this should be a part of theorem. There should be an assumption.
Well, it is an assumption. Assumption is in these letters. Tomek, assumptions in these letters. He just mentioned that he has no time to define it.
Yeah. I will define it later.
Yes.
Okay.
Yeah.
So in other words, you can define the subcategory separately before this theorem and then form this theorem. It would be
okay. Let it be. But it's not okay. But let it be. Okay.
Yeah, maybe the statement's not the best way of writing this, because of course the existence of a subcategory, it's kind of a little abstract, but there's a category.
But you see, there is a subcategory is not so completely trivial, because you have to prove that these conditions that we cook up to ensure that we have a star homomorphism when we take this formula is not at all obvious that they're composable.
So maybe, Thomas, the thing that you have problem with is the following, that in this theorem, the formulation starts with there is subcategory.
Yes.
So there is, the subcategory is under a small quantification. So therefore, it wouldn't be concrete in this formulation. Quantified,
exactly.
Sorry.
Exactly.
But once it is constructed, from this moment, it is a very concrete construction, and then the theorem could be formulated for this category.
Yeah, but is this a unique subcategory of some property or not?
No.
Okay.
Yes.
So in some sense, I will agree with you, Tomasz, if you have problem with this name of this category, if this theorem is formulated like this, where the existence of this category is in this quantifier. So in some sense, you quantify over something which has very long name. So probably this is...
But I hope it's clear now, so let's go on. Let's go on because it's clear now.
Because otherwise you can just take one graph with just the identity, then that's the subcategory satisfying this property.
Exactly.
Okay, so the other notion of morphism between graph is this notion of path homomorphisms. And then the idea is that this morphism of graphs or homomorphism between graphs is now it's a mapping between finite paths on E and finite paths on F. And then we want to preserve vertices, so send vertices to vertices. And again, we want this to be compatible with the source and target maps. Now the source and target maps is the one for paths. And we want this to preserve the concatenation of paths. I'm going to write this in the remark. Basically, we're just thinking that FPE and FPF are categories, and this is just a functor. So just to give an example where this appears, so I talk about the quotient of the Topliss algebra to the circle algebra, and then we can also see compact operators inside the Topliss algebra. So, and then
Exactly, yeah.
this graph where you have infinitely many edges going from one vertex to the other, and then you have the graph of the Topliss algebra. And there is a way of building this path homomorphism where you just take one edge and send it to this edge. So vertex is just gonna go to in the way they appear here, and then from, let's say you enumerate the edges. So the first one go to this one, and the second one you just take one time the loop and then go to this other edge, and then the next one go 2 times the loop and then this edge, and so on and so forth. So this is gonna give a path homomorphism, and then of course we're gonna have this analogous theorem, but this is the homomorphism of graphs, so it's different from the other one. And now it's a covariant functor because it's gonna go from the compact operators on a separate Hilbert space to the Topliss algebra, and this is going the same direction of the graphs.
Well, I would say that this is minimal compactification of compact, minimal unitarialization. So this is a spotless sphere, yeah.
Yes, of course, because it's a finite graph, yeah.
May I have some comments to this definition?
Yes.
Oh.
It would be maybe more succinctly to say that it's a functor between 3 categories generated by these graphs.
This is what he said.
Yeah.
He said it.
This is just a remark that it's here.
He just said it, Tomek. You are not listening. He said it.
No. I must. I hear very strong echo. So maybe I lost it. Okay. So
it's in the remark.
So why not to say this instead of this definition?
Because it's explicit. I always say both.
Yeah, but it's repetitive in displaying all the ingredients of something which is a simple notion. But okay.
Because this definition does not need the person to know category theory, I guess. Yeah, it's directly from graph. So if you want to talk about it just combinatorically, we don't need to talk about the category.
Exactly.
And we can relate this notion of path homomorphism with the previous one. So there's this one correspondence between path homomorphism that preserves the length and the homomorphism graphs as before. So before we just send edges to edges and vertices to vertices, but there's a natural way, because the map before preserves the source and target, it's compacted with source and target. If you have a concatenation of edges and you apply well, let me go back here to the other one. So if you have a concatenation of edges and you apply phi1 on each edge, because it's compatible with source and target, it's going to be a path on left. So there's a natural way of defining, extending these to paths. And so there's this one correspondence between this homomorphism before and this path homomorphism of graphs. In fact, we can see OG as a subcategory of PG in this
now I see.
way. But I'm not going to use this here because when you go to the functoriality, actually we don't want to see OG as a subcategory of PG because one is contravariant and the other is covariant. So it's
exactly
a different nature.
Exactly.
So just to simplify notation, because we want now to talk about paths and not only edges and vertices. When we talk about a graph system, which the star should be above, we have the partial isometry associated with each path. If it's a positive length we just take the multiplication of each partial geometry associated with edge. And if it's a vertex, and then it's just the projection of it. So we are gonna now, from now on, just write S of X to mean not only the partial geometries, but this multiplication and the projections. And now, again, this is not the best way of writing it, but there is this category of PG, which is injection vertices, monotone and regular, and proper. No, proper, no, don't need proper here. It's injection vertices, monotone and regular, so there's the subcategory of PG. And now, if you have a morphism in the subcategory, the definition of the star homomorphism is covariantly, so it goes from C star of U to C star of F, and then you just take this X, and then you just apply theta to this X, and then this is the partial geometry associated with this theta of X. And again, this is going to give a functor from this category of a regular monotonic injection versus path homomorphisms to the category of sister algebras.
So here, let me quickly comment, if you don't mind, that here the tricky part is regularity. So one really has to fight to ensure that this second Kunstfigure relation, the last Kunstfigure relation, which is only for regular vertices, is preserved. It's kind of tautological when you preserve a length of paths, and this is what you can find in books, or at least in this famous book of Gene Abrams and others. But when you go from just length preserving path homomorphisms to more general ones, like in an example which Gilles just gave you with the Teplitz algebra and the minimal integration of compact operators, well, it's a bit tricky. How do you preserve this regularity if you are now mapping edges to paths who might be much longer than of length 1? And that was the tricky condition that had to be somehow discovered. And I repeat here, you should bear in mind that because we do not preserve a length of paths, we are by no means equivariant. We lose equivariance for the gauge action. And also, even if both sister algebras are unital, so even if there are finitely many vertices in E and F, we no longer need to be unital. Okay? Sorry.
And then that's the main question that when I started working on Piotr that we wanted to answer, is that we have these two functors, one is contravariant and then the other one is covariant. And how do you define just one functor, I guess, from these two? Of course, one of them should be gonna need the opposite category, so we have it both in the same direction. But then the question is, how do you unify this? And then the same thing happens for groupoid sister algebras. So groupoids generalize both groups and topological space. In topological space, you have a contravariant functor. For groups, you have a covariant functor. So how do you unify this? So we got inspired by this problem from groupoids to define this notion of morphism between graphs. And one approach of looking at in the groupoid setting is looking at relations. And so that's what we do here. That's how we unify this. We're going to use relations to unify these two functors. So that's the notion of a morphism in general for graphs. So when I talk about relation, it's just a subset of this Cartesian product. In the case for a relation morphism between graphs, it's actually going to be a relation between paths of graphs. And the conditions that we want, the first one is that we want the pre-image of vertices to be vertices. So whenever I have anything in the relation, say the second entry is a vertex, when the first one to be a vertex. So for a relation, we can easily define the pre-image and the direct image for the relation, the same way that we do for functions. And then we also wanted the relation, since we're working for graphs, we also want the relation to preserve sources and targets. So if we have a pair that's in the relation, the pair of the sources should also be in the relation, and the paths, the pair of targets should also be in the relation. And so we can show that this composition, that is the notion of composition of a relation, which is also in general for relations, but then with this composition, we've shown that this is actually a category, which we're gonna denote by RG. So relations, morphisms, and graphs. And we want to see the other categories as a subcategory of RG. Of course, one of them is going to be actually in the opposite way. But so if you have a homomorphism of graphs, we just define the relation of, which is just the graph of the graph, not graph as a function, like the graph of the function of the graph of phi. And for theta is the same thing, but actually is we take the inverse relation of the graph. Should be r theta, should be so, and so it's also the graph, but we have just take the inverse relation of the graph. And we can see that actually, so this embedding of this category of G, and then the opposite category of G in RG, which is just take a graph itself, and then the morph phi to this relation of phi, and then the morph theta to this R theta. And the embedding, since it is the opposite direction, or we can think there are functors from OG and RG, which is covariant, and a contravariant functor from PG to RG. This is another way of thinking. Okay, so one of the questions that we wanted to consider is are we adding something new in a sense? So we have a relation for homomorphism graph, we have a relation for path homomorphisms, and now we have this bigger category where we can compose these two things. Can we generate anything new which is not coming from these two subcategories? And here the answer is no, actually. So we can always factorize a relation using a homomorphism graph and a path homomorphism of graphs. And the idea is to construct this relation graph, which is basically saying the set of vertices is basically the relation on vertices, and the set of edges on this relation graph is basically how edges on F are related to paths on E. And the source, we have a source in each of the in each entry, and just apply the source of and multiple source and targets. And so we went to kind of decompose the relation. Actually, we need a little bit more than just the relation. We want the relation to be multiplicative and decomposable, because now we want to look at path algebras and so on, the compact algebras, left path algebras. So we want the maps that we defined before to be multiplicative, and so we have these two notions. So the first one is that if you can concatenate the paths in the relation, both in the first and the second entry, then the composition is also going to be in the relation. And the second one is that if we look at the second entry and have a concatenation, the second entry that is related to something in the first entry, then this first thing in the same first entry should be decomposed in also in concatenation. So the first one is related to Y, and the second one is related to Y prime. So basically, this is saying that we kind of take the relation and basically factorize using this graph here. So this is needed to define if you want to do to the previous step, going to just path algebras, this is needed to define a functor to path algebras. But here I'm just gonna talk about the factorization. So whenever you have this any relation morphism, which is multiplicative and decomposable, then using this graph relation, and there's two natural maps that we can define from E to F, which is just taking these projections. So we're going to have these two morphisms between one, this theta is going to be a path homomorphism, phi is going to be a homomorphism in the original sense. And then we can decompose or factorize the original relation using these two morphisms here. So in a way, this category that we define is kind of generated by both OG and POG output. When we go further, and then we go to the, I'm going to put this as a question in a slide later, but we don't know if you go to the category that we need for the functoriality of system algebra, we don't know if we can always decompose or not, or not factorize or not, but we know that we cannot always factorize into. This is going to give an example. Okay. And also,
so I have a question.
yes.
Speaking about this decomposition, there is some general theory of decompositions like this under the name of factorization systems.
Okay, it's interesting.
Can you say if your decomposition satisfies these requirements for this notion of the factorization system?
I'm not familiar with factorization system, so I'm not sure. That's what
But Thomas, you can show it to me in Warsaw. I'm very interested. Show it to me in Warsaw and we check it, okay?
Janelita was speaking about this.
Yeah. But we don't, at the moment we don't know what it is. So let's not waste time for this. But it's a very interesting question. So let's settle it on Friday.
And so the other thing that we were also showing is that if you already know that R is factorizing into these two relations coming from homomorphism phi prime and then path homomorphism theta prime, then we kind of have this universal property of this relation graph that we can define a homomorphism of graphs. And here this pi is a homomorphism of graphs between this the one that we can decompose and then the relation. So there's this universal property of the relation. Basically, this is saying that if you have a multiplicative and decomposable relation, then this relation graph gives the whole information about the relation.
Now, let me quickly comment, because this was what I was discussing at length with Jack Spielberg. And this looks a little bit like the universality that you have to define a pullback. And in this case, it is almost equivalent to being a pullback in the equivalent sense, but not quite. Not quite. It's not true. It's very close to being, like a pullback property, but it's not a pullback property. It's because you cannot always decompose this R into an agreement of two arrows going down, and that's an issue. Yeah. And that's an issue. So it's very close. It looks like a pullback universal property, but it is not.
Yeah. And also these two maps are kind of in different flavors. So
yeah, exactly. No, that's another. But this you could somehow reconcile,
Yeah.
But the point is that here we demand compatibility with R, and R is like a composed map, and it's not true that you can always decompose it.
Yeah, that's true. Okay, so now we want to build the subcategory. Now we're going to be really specific which subcategory that we're going to talk about. So we have this notion of unmissable relation graph, and in order to, again, we want to find a functor from the category of graphs, and now this notion of unmissable relation graphs and the sister algebras. I'm going to say how from a relation we define the map, but for now, let's just see what properties that we need. So the first two already appear, so we want this to be multiplicative and decomposable, because we want the maps to be multiplicative, and we need these two properties. So the next one is properness, because we want, let me write here, and it's gonna appear later again, but we want to define, it's gonna be a contravariant functor, so it's gonna be from the C star of F, C star of E, and it's kind of like in the case of homomorphic graph that you want to use pre-images. So R star of F on Y on F is just gonna, we want this to be the sum of all elements that are related to Y. So the pre-image of Y as Y or S at C. So I'm gonna write this is a formula is gonna appear later, but basically want this formula to be a star homomorph of C star algebras. And the first thing is that we need this sum to be finite. So
Exactly.
it's definition of properness.
Yeah.
The other ones, it's also to ensure that this is going to give us a star homomorphism. So the next one that we want is to be a partial function on vertices. So for a vertex U in E0, it might be that U is not related to any other vertex on F, but if it is related to a vertex on F, so this is the only vertex that it's related. So we have this condition. I think the version archive is wrong because there is no intersection of 0.
Exactly, and there is a very simple counterexample. You can have a graph which is just one point, and you can have a graph which is just one loop. And then this vertex is in relation with all the paths here. So path of length 0, which is a vertex, only one vertex, path of length 1, path of length 2, you know, so this if you want the image of this one vertex, it's actually infinite.
Yeah.
But when you intersect with vertices, yes, it's in relation with one vertex only. It was a typo, okay, simply.
Yeah. Okay, now I forgot to put a pause here, but there's two conditions here. So the other one is this target bijectivity. So whenever you have an edge on F, so the edges that are related to F and the vertices that are related to the target of F should be in bijection using the target map of E. So anything that's related to anything that's related to F that's arriving at some vertex which is related to the target of F should be there should be a 1-1 corresponding to these two things. The other one is this monotone, and so if I have these two pairs that are related, where this F and F prime are actual edges. Yeah, I think I forgot to write here, but if these two things are edges, R1 is the edges of the regulation. So if one of this is, I guess we could write this as comparability. So if one is initial subpath of the other, then actually these two pairs should be the same.
Yes.
So once again, R1 is what?
These are edges in this relation graph, which means
Edges,
basically
okay.
that F and F prime are edges.
Okay.
Yeah. And finally, the regularity condition. This is a little bit the one that's a little bit harder to understand, because even for this bad homomorphism, it's a little bit hard to understand. For homomorphic graph, it's easy, just in the pre-image of regular versus irregular.
Exactly.
For path homomorphism, a little bit trickier, and here is also a little bit tricky. So what's the idea here? So you have this regular vertex B, which is a vertex on F, and you have a vertex U on E that is related to V. And now let me try to write it. So we have a certain U here that is related to a certain V over here. And now you take any path starting with U, like any path X starting in U. So this is a concatenation of V. This path should either be an initial subpath or they should exist as a path of X that is related to some edge leaving from V. So there are finally many edges leaving V because V is a regular vertex, finally non-empty. So there are finally many here. And the idea is any path starting in U should have either initial subpath or this X is an initial subpath or something related to X. So this is the regularity condition. For those that are familiar with inverse groups, basically what it's saying here is that the set of edges is a cover for V, and somehow the kind of the pre-image of this X should give a cover for U. In this notion of covers for inverse group. But yeah, that's the condition that we have.
Just let me emphasize one more thing because it's very easy to overlook. Here's an implication, okay? Here's an implication. So we are not saying that if you take a pre-image of a regular vertex, it has to be non-empty. It might be that there's nothing in the pre-image of a regular vertex. Moreover, if you look at the pre-image of a regular vertex, it might happen to be a sink, okay? So it might happen is that such a U does not exist, and if it exists, that there's no path which is emitted from there. But then it's automatically satisfied because when you have something which is false, implies everything. So the implication is true. We only have to sweat a little bit when both U exist and it's not a sink, so a path exists. Then we have some conditions. But I want to alert you to the fact that we have real life situations in which, for instance, U exists, but it's a sink.
Okay, so just going back to this other category that I had before, so CR, TB, POG, and you had R and IPG. So now we have the terminology here. So it's R is irregularity, both in these two settings. So this is regularity here. This M here that appears monotone, so this is the monotone that appear here. The TB that appear here is the target bireactivity here. This injection vertex is because we are using the opposite category inside the RG. So this injection vertex actually appears as this being partial functional vertices. And then have this P properties here. So the lattice that doesn't appear in the others because it's automatically satisfied for the relation that we have. So target bireactivity here is automatically here, being injection versus automatically here, and vice versa. So the lattice that do not appear in the other categories is just because it's actually automatic. So this is the notion that we have. So as I said, so the subcategories should not be quantified there in the theorem, but this is the subcategories that I was talking before. So it's just the ordinary graph homomorphism intersection of the dimensional relation graphs when you have the inclusion of OG in RG, and the other is in the opposite category. So if you have the inclusion of the path homomorphism opposite inside RG, so if you take the intersection of this admission relation, then that's the category that we had before. And well, and then the admission relation is actually a subcategory of RG.
Let me, can you go back so that I have some room to write? Yeah, no, just to have half empty space. Yeah, that's perfect, thank you. Because it might be interesting to category freaks like Tomek. It was very surprising for us, remember, Gilles, Francesco, when we were thinking about the intermediate category. So you skipped it, but we have this category which is POG, which means only proper graph homomorphisms. Yeah, so you have POG, and this would allow you to induce homomorphisms between path algebras. okay? And when you have this category IPG, which is path homomorphism of graphs, which are injective on vertices, which allows you to induce covariantly homomorphisms of path algebras, okay? But we proved that there is no common denominator. There doesn't exist a subcategory of ARG containing these two guys as subcategories. I mean, of course, this is taken with op, yeah? And this is kind of funny because everything is already better when we add one more condition, but we proved that there is no, you cannot unify POG and IPG op in this relation category. There doesn't exist a subcategory of subcategory of RG, okay, which would allow for a puncture to algebras and algebra homomorphism, such that the construction of path algebras would give you this functor, and you'd have these two subcategories of special cases. It just does not exist. We have an argument that it's not possible. Sorry for the interlude.
So yeah, so now the theorem, I guess. So now we can build a functor from this subcategory of admissible relation morphisms.
There is something missing behind this sign of summation.
Speak louder.
There is something missing behind this sign of summation.
Yeah.
The
Yes,
SX, yes.
Yeah, SX, yeah.
Yes. Well,
Yeah,
this
it's
was
an
left for the
overlap.
imagination.
Yeah. As an exercise.
Yes. Complete the picture.
Yeah.
Yeah, so we take the relation R. At the beginning, we are defining a covariant functor because relation we can just take the inverse. So we have can choose if you want to be either a covariant or contravariant functor. But we decided to be a contravariant functor because we want an inclusion to be a morphism in this category from E to F. So if E is a subgraph of F, then the relation associated with the inclusion, we want it to be a relation between an F. And in the previous version that we had, they actually go the other way. So when later we go to the pullback theorems, which we're going to do this next year, then we prefer this the inclusion to be in the same direction of the relation morphism. So that's why we chose to use a contravariant functor here.
We want to think about graphs as quantum spaces, kind of mimicking Gelf and Neimar.
Yeah. And so this formula gives a homomorphism of a star homomorphism of graphs star algebras. So we need all the condition properties, all the stuff, and regularity to show that this is actually a well-defined star homomorphism. And then we have a functor from this RG to the category.
Nie wytrzymał do końca.
Okay, so I was talking about this factorization of relations. So every relation can be factorized into a relation from OG and a relation from PGO. But can we do the same thing for admissible relations? So, well, we already kind of have this decomposition, which has that universal property. So we can ask, is the decomposition in RG preserves the admissibility? And the answer for that actually is no. So in general, the factorization that we had before does not preserve admissibility. So I'm going to show an example. Now I can use the graph that Francesco drew. So this is the relation that we have. So vertices with the same number is going to be related to its kind of itself, but we are also going to relate this vertex 6 to the vertex 5 here. So 6 is also related to 5. And as far as edges goes, because we need to preserve targets and sources, this edge from 1 to 3 it's not going to be related to anything. This edge from 1 to 2 is going to be related with itself, and
Indukcji nie możesz ładować.
and that's the only relation that we have. So we could, we don't have a loop here at 5, so there's no place that we can relate this edge 5 and 6 because there's nothing connected 5 to 5. So there is only one path here that is related to or one edge here which is related to this edge here. And then we shown that for this relation, when we take the decomposition that we had before, this is not admissible, and actually we can show that there is no other, because of this inverse property, there is no decomposition using our phi and our theta. But we also show in the other way around, it's also not possible to factorize. So it cannot be. We cannot write this as being admissible in both directions. So both like this. It is not possible to do this, and you also can decompose in the other way. Both of these cannot happen. But then we show that actually can decompose in or factorizing through three relations. So we don't know if you have any relation, if you can always factorize in this way using just relations coming from homomorphism and path homomorphisms. We have an example here. We try to work out some examples, but so far we don't know if either we can always factorize or if there's an example that we cannot factorize. Okay, so I think I have around 20 minutes. So this is the work that I done with Catarina and Francesco. And as I said, there is a simple example that if you start of a relation, and then we have sometimes you can even have an isomorphism between the algebras. I think one of the examples that we had before, let's say you have these two graphs. But it in this direction. It should be the other way, right? Should be the other way around. So these two algebras are for these graphs, 3x2 matrices, and there's a relation, natural relation in one of the directions that is going to give the isomorphism between the 3x2 matrices. But the inverse, we need to send some kind of e to things using a star. I don't remember exactly what was the thing, but we basically need the star here. And if you look at the formula that we had before, over here, there's no star in this sum. So we cannot send a partial isometry to something using stars here. Just, the definition that we had before. So we are trying to think about how we can do this. Then one approach that Half was saying is trying to use using groupoids. So I'm going to briefly talk about the groupoid picture. I don't want to go too much in details because I don't have too much time. I think Elias talked a little bit about groupoids last week, and it's a kind of that rather appear, I think, in the seminar a few times. So groupoids
probably you meant axiom similar to that of groups instead of graphs, yes?
What do you mean by that?
The last word, right?
In the third line.
Yes, groups.
Groups.
Last word.
Yes.
So groupoid just is a small category for such that every morphism and isomorphism, or we can think as a set of partially defined multiplication and inverse, which is associative, and there's units that not just one unit, there are several units, and then you have an inverse as well. if you want a topological groupoid, then we assume this G has topology, then the operation should be continuous. Usually, if you want to use in the setting of operator algebras, you want the units of G to be locally compact in Hausdorff.
Sorry, just a quick question. You also assume your target and source map to be continuous, yes?
This is a consequence of the multiplication inverse, because the source and target is just a multiplication with the inverse. So the domain of x is just x minus 1, x minus 1x, and the other one is so it's just a composition of continuous functions. So it's automatic. But yes, they are continuous as well. So usually in the setting of sister algebras, we want the unit space to be locally compact Hausdorff, but there are other settings that we don't actually need this. Just a topological space. Then we have this notion of an Italic groupoid, because it's a little bit easy to define a sister algebra for Italic groupoids. And then for Italic groupoids, we want this to have a basis of open bisections. Sometimes the definition of bisection is already implied that it's open, but if you want to work in one more general setting of groupoids, we can just talk about bisection as being a subset of G, so the domain and the codomain maps are injective. And then open bisection only when it makes sense for you want to have a topology. And then you have an ample groupoid, which is an Italic groupoid. One way of defining is just saying that the unit is locally compact totally connected Hausdorff space. And for ample groupoids, we can define not only the sister algebra, but you can also define the Steinberg algebra, which is the algebraic counterpart of sister algebra. And then we can, this is one of the earliest paper connecting these two things to paper Elise and others. They kind of independently define the algebra of groupoids from Steinberg, but then they later did reference to Steinberg as well. But there they study left path algebra using groupoids. So we need an ample groupoid for the purely algebraic setting, because we want the characteristic functions of these basic open bisection, but then it's going to be compact open bisections to make it sense, be continuous and anything like that. Anyway, so
probably I didn't catch the word. You said about the construction of a sister algebra, and you mentioned also the construction of
the Steinberg algebra. So this is the algebraic version. So have a groupoid G. There's this construction of the sister of G. But if G is ample, there is you sometimes use the notation R, AR for G. So it's kind of mimicking the construction of the sister algebra, but now it's just an algebra. So have R as a unital commutative ring, and then we can define using characteristic function of certain compactable bisections. We take this as the sub-algebra generated by G to functions from G to R. Use this first as a vector space, and then you use the multiplication, the convolution product as used for C star of G.
Sorry, could you repeat the name, how it is called?
Steinberg.
Steinberg, okay.
Steinberg algebras.
But it's funny, in Wikipedia, all I can find are the Steinberg representation, not an algebra.
Yeah.
Steinberg module, Steinberg character, but not Steinberg algebra.
Sometimes it's called groupoid algebra, but the groupoid algebra, people from algebra study is kind of G having the discrete topology, and then what Steinberg did is that there is the inverse group algebra, and then you need the topology of the groupoid. You have the universal groupoid of an inverse group to study the algebra of an inverse group.
Oh, I found it. Graded Steinberg algebras and there, blah, blah, blah. Yes, okay. Yeah.
So this is something in between, yes? More than purely algebraic, but less than sister algebra. Am I right? Or?
I mean, it's an algebra, but it's an algebra built from a topological object. But it's just an R algebra. And we can make it as a star algebra if R is an involution. There is also a natural structure for star algebra as well. But at first, it's just an algebra. And if R is the complex numbers, then this is actually dense star algebra.
Yeah.
Okay, so we want to define a groupoid from a graph. So for that, we need the boundary path space of the graph. So the idea is that we're gonna take not only finite paths. Yeah. Now here, this IP I haven't defined this to be infinite paths of E. Sometimes it's called E infinity. So take all infinite paths on E, and we take all finite paths. It should be a target, not our range. That ends in a vertex which is not regular. So it ends either in a sink or in an infinite minimum. And there is a natural way of defining the topology using cylinder sets, but it's not just cylinder sets. It's a little bit more tricky than that. But there's a topology on this boundary path space, making it locally compact, totally disconnected Hauser space. And for the groupoid, the idea is that we gonna take it's kind of we call this the tail equivalence. So we have two elements in the boundary path space that ends to have the same tail of the same elements in the boundary path space. And X and Y here are finite. So X and Y are finite paths. And then if you remove X and Y, you get the same element in the boundary path space, which is this Z. And then in the middle, we count how many times we need to remove. So count the length of X, and then you subtract from the length of Y. And then the operations, for those that are familiar, this is a very natural operation. So it's only defined when the third coordinate of the first element is the first coordinate of the second element. And then when this is, you just remove this y from the middle, and then we sum the elements of the integers. And then you leave x and z as they are. And for the inverse, we just flip x and y from places, and then we take the inverse of k in z, which is just minus k. And then again, there's a subtotal topology that makes this an ample groupoid. Then we can show that the sister algebra of this ample groupoid is the sister algebra of the graph, and the Steinberg algebra of this ample groupoid is the left path algebra of the graph. And so the idea is that if you want to study homomorphisms between the graph sister algebra.
Gilles, if you don't mind me asking a stupid question, so who discovered this? Who proved it first?
So for graph sister algebras, I think in the definition of a graph sister algebra is already using groupoids, which is the paper by Vesk, Rayburn, Renault, and Kumijan. But there they ask the graph to be row finite and so they just use infinite paths. Then the general version was done by Patterson using inversion groups. So he defined this boundary path space. I don't think he called it like this, but it's in the paper by Patterson, where in the general setting for graphs, this sister algebra graph is this groupoid sister algebra.
Can you say the name again? Patterson?
Patterson, yeah. I think it's Alan Patterson, yeah.
Where is he from? Which university?
I don't remember, but he has a book on groupoid sister algebras.
Okay, so it's more from groupoid sister algebras. Okay.
Yes. From groupoid in inversion groups. And for the Steinberg algebras and the left path algebras, this is the paper that was commented by Lisa, Clark, Adam Sims, and Cynthia Farfin, I think. And Tom Ford. I think this is here are 4 people. It can kind of independently define, but as I said, they cite the Steinberg's paper, but they define this for left path algebras. And so the idea, so this is a notion that Ralph came up with because he has this notion of actor between groupoids, which is kind of a correspondence between groupoids, but then if we just want to look at star homomorphism, just these actors, and the idea that we want a kind of a functor from the groupoids, ample groupoids or topological groupoids, italic groupoids, I guess in general, with these morphisms to give a functor from the category of groupoids to the category of sister algebras. And then he tried to translate this when we have a graph, what do we need to get these actors? So the idea is that we have a graph E, and then we have this groupoid H, and kind of instead of have a Kuntz-Krüger family on a sister algebra, we have this E family in the groupoid. So the idea is that we're going to have for each vertex a compact open subset of the units of H, and for each edge we have this compact open bisection on H. So and then you kind of want the relations from the graph sister algebra to be translated into relations between these sets. So the first thing is that the intersection of these two sets should be empty if the vertices are different. So this is just saying that the multiplication of projection is 0. The second one, here is the D is for the domain in the groupoid. So the domain of this bisection should be the semi-compact subset of the range of phi. So as I said, here is mixed because we are using two different conventions. I think in the paper for off is gonna appear as here. And the same thing for the range. So this is kind of similar to that relation that we had for in the definition of graph sister algebras or left-graph algebra, that projection.
Sorry, in the second condition, you have one equality and one inclusion. Is it correct?
Yes, because
It should be like that, yes?
No, that's correct, yeah. Because in the definition, not the definition that I gave, but the definition that people use for sister algebras, sometimes they write that SE star is less or equal than projection should be the source of phi here.
Yeah.
So this relation is this inclusion here.
Yes.
Okay.
It's inequality of projections.
Yeah,
Yes. You have equality of projections.
Okay.
And in SE star or SE star C is the projection.
It's equal. Yes. Yeah. Exactly.
Okay.
Yeah. Very
This is
good. Very good.
the inclusion.
Thank you.
Yeah. Very good. Mhm.
And then this is just saying that the third one is just saying that SE star SF is 0. So this is the range of these two bisections empty. And then we have the regular condition. So this is a consequent relation. As I said, I'm not 100% sure if this is correct because I was using the other convention for graphs in the paper, and I'm not sure if it should be R here, should be D, but anyway, it's basically we're just translating the definitions on the algebra to the relational graphs. And now we want to define from a relation this family from one graph to the other. And for that, we need these cylinder sets. So first, for the bounded path space, this ZX is just the all paths that has X as an initial subpath. And
so what is gamma? Should be E probably, yes?
Yeah, it should be E. Yeah, it's just that in the paper we are using gamma, but yeah, it should be E here as well. And then it should be calligraphy G. And you have the same thing for in the groupoids. You take two finite paths that ends and should be target that end at the same place. Then we just take all elements that has X and Y as initial subpaths in the first and third coordinate. And then there's the theorem that we have is that you have two graphs and you have this admissible relation morphism. Then we can define basically using the same formulas, thinking that this is the projection on V, this is the projection on U. So we have the projection V should do, or the map from V to the other algebras is this one. And the same thing for the bisections. So this should be the bisection associated with each of these pairs that are related to R. And so these families is this dynamic conscript family for in G of E. So we start from F and then go from E. So from this relation, we have the other definition. And then from Rolf's theory, then we can define a homomorphism between the graph system algebra using the theory of groupoids. But now I haven't written here, but the example I was talking about, the inverse of matrix, actually we can define this. I haven't written this yet, but we can define actually this family for the inverse of relation using stars, because now here, because we are using these bisections, actually this Z of X should kind of be thought to be S of X, but we also can do the same thing in the groupoid in the other way around, Z of X, X, and then this should be kind of be the star. So because we have more structure to work with, we can use this bisection. We can use the stars here as long as we choose the correct bisection. And that's it. Thank you.
Muito obrigado. Perfect timing. So any further questions? Adam.
Maybe it is too vague to pose it as a question, but Piotr, you mentioned that you want to think about the graphs as some sort of quantum space, yes?
Yes.
And I wonder, there are some results about convergence of graphs. And I don't know whether it could be somehow incorporated into this business, but it's just a vague idea. I don't know.
But it's not a bad question. So I understand that it's a question to me. So if I allow me, I will answer. You see, it's part of our network project, and here these are people like Frédéric Latremourier, maybe Ante Shitash, who are thinking about such things, but mostly Frédéric. And maybe also Carla Farsi, I don't know. But definitely Frédéric is here, the chief of this metric convergence. Exactly, because you see, somehow doing spectral triples on graph sister algebras, as far as I know, is not that easy, because the graphy presentation of sister algebras is more related to K-theory than to any smooth structure. That's my vague opinion. But when it comes to metric properties, in the sense of non-commutative metric geometry started by Riefeld and so beautifully developed by Latremourier, this is perfectly good playground. And I believe, I don't remember, Francesco, maybe you remember some results that were listed in our report. But if there are no concrete results already, then at least people are working on it. So having the concepts of convergence, yes, it makes sense. But you have to somehow introduce some equivalence relation on graphs, because you can have many different graphs that give you one and the same sister algebra.
Okay, I see.
But you can divide by such an equivalence relation, and then you can try to develop the concept of convergence of graphs. And yeah, I think that in this precise wording, which I just put and you suggested, there is no result as of yet. But somehow people are inching towards this direction.
Okay, very interesting.
So I think, Tomek, or Atul, I don't know which one of you.
Yes. So I have a question about the interaction between graphs and groupoids.
Yes.
So it is known that this graph sister algebra is a groupoid sister algebra.
Yes.
And then whenever you have, for instance, the Zakrzewski morphism between groupoids, you obtain homomorphism of sister algebras.
Yes.
Okay. And you are proposing a different kind of relation between graphs. So my question is, can you compare these relations to Zakrzewski morphism between groupoids of these graphs?
Yeah, I think there is a way of doing. I'm talking to Ralph about this because we are using this notion that because Ralph actually works in a more general setting of correspondence in between groupoids, and then the correspondence between groupoids is going to be correspondence between the C-star algebras. But then if you restrict the correspondence to this class of actors of groupoids, then actually the correspondence between the C-star algebra is going to be a star homomorphism. I think when we restrict these two actors, there's probably a way of going from one to the other, and actually it's just two different ways of looking at the same object in a way. But we still work on that, on exactly the nature of these two things.
I don't understand the different ways of looking at the same object. But what is this object are you talking about?
You talk about this, or I don't know how to spell this Zakrzewski.
Zakrzewski.
Yeah.
I mean, it's such an easy name. Come on, I'll write it for you. Yes.
So on one hand side, we have Zakrzewski morphisms between groupoids of these graphs.
Yes.
On the other hand, you have these relations between graphs.
Yes.
So my question is, can you compare?
Yes.
They as I know, as correspondences, for instance.
Yes. So as I said, there is this notion that Ralph has of actors, and here I think there is kind of a one-to-one correspondence between actors and Zakrzewski morphisms. I think that
So it's one side. It's one side. Okay. Can you compare your relations of graphs?
So here we have this one-to-one correspondence, and then this last slide that I was talking about, this one here, is just saying that if you have a relation between graphs, then we can define an actor between the groupoids.
Okay.
So from a relation, we have the actors, and from the actors, we get this Zakrzewski morphism. So we actually, yes. So from a relation morphism, we should be.
So this is one-to-one correspondence between relations and Zakrzewski morphisms.
No, that's no. In general, no. Because relation on graphs, we are asking that let's say an edge or an edge f here is related to a path x on E. So I have E here, and you have F here. So an edge is always related to an x. But when we go to this more general setting, this F here it should be that it should be the bisection, which is here F is S of F. And this bisection via this morphism actually could go to something which is not actually a bisection of the same nature. You could have a different kind of bisection. So not all relations or not all morphism in this setting is going to be given by relation. This is more general than what we have.
Yeah.
So what is more general and what is more special?
Our relation morphism is more special, and
okay. So your relations are special. It's a special case of Zakrzewski morphisms.
Yeah, as one should expect.
Yes.
So you are not sure yet?
Well, we are checking it.
We are sure. We are sure.
This you are sure. Okay.
Yeah. Because, as I said, there are some examples, for instance, for matrices, that we can actually look at the homomorphism between the graph system algebra from this point of view, but we cannot look at it as a relation morphism. Because we want in the sister algebra setting to send something like E to some SF star, and this cannot be done using relation, but this can be done using Zakrzewski morphisms. So this is more general.
Okay, any other questions? And by the way, I honestly don't understand how we can have problems with spelling Zakrzewski. You write it exactly as you hear it. Okay, silly jokes aside, any other questions, anybody? Richard, are you happy? Young?
I'm happy.
Okay, so in this case, let us obrigado our speaker again. Thank you so much, Gilles.
Thank you.
Thank you.
I stop the recording.